Hey logicians, this is your Professor O'Million Chuck here to talk to you about homework 3 and how to do it. Alright, so this one's actually kind of tricky. I'll go over some of the tricky parts. But one thing I want you to just note straight away is that we're going to be using CL, our really simple conditional logical language that only has 2 assertions. So just keep in mind that these things are false. If and only if, right, the antecedent is true and the consequence false. We've gone over that many times. And there's only 4 possible models, right, or ways of assigning T and F to P and Q. All right, so that's what you're going to have to do here in this very first section, all right? Also note this, you do not have to check more than one on these questions, right? These are mutually exclusive. And a little tip, logically false is simply not an option, okay, at all in CL. It just doesn't have enough expressive power. There's no negations, so we can't express anything false. Right, so you're going to be deciding on whether or not stuff is logically true or logically contingent. Right? So what do those things mean? Well, you have to remember logically true just means that it's true in every single model. Right? And so this is just exactly that kind of thing, all right? And if you think about it, that is the case, all right? And you really only need 2 models to show you why. I mean, make P true, all right? Well, then that means P is true over here. But then if that's true, this whole thing is true, okay? So that ends up being true. And then if P is false, okay, well then this is false, but then the whole thing is true because there's a false antecedent in this whole thing, right? So it doesn't really matter what you assign to Q. The models of P are what determine its truth value, and it ends up being true in every model. Okay, so it's logically true. Not so here. Right? If this one's just logically contingent. That means that there is at least one model where this thing is true, and at least another one where it's false. So you got to look for 2 to see if it's contingent, right? It's not going to be logically false, okay? So if you find one in which it's false, all right, then you can know that it's not logically true. It's certainly not logically false. It's logically contingent, okay? So the idea here is to test maybe for falsehood. Again, that's what we like to do in this class. So can you make this false? Sure can. Right, logically contingent, right? Okay, so you need to do that for all of these, okay? This one is the beast of the bunch, as you can see. Really, though, I think if you just kind of look at it, it's going to have something of the same kind of form as this one. Right, we got an antecedent that shows up here. And we got an antecedent that shows, or a consequent that shows up here that looks an awful lot like the antecedent, and then we got this kind of just, premise just hanging in here, or this assertion that's really not doing anything. All right, so decide on what that one is. All right, if you can't figure it out from what I'm saying, then just go through each model and test it and see if it always comes out true. If it doesn't, if it comes out false in a case, then you know what to mark, right? So that's how you do those problems. On to question 2. We want to indicate which logical properties apply to the pair of well-formed formulas, all right? So these are all relations between pairs, okay? Now, this is the confusing one, entailment, right? If you don't understand this, you certainly won't understand this, okay? Because entailment goes both ways in equivalence. So we need to get a handle on this, right? Now I'll get to that in a moment, but let's just look at consistency. Consistency is just the idea that there is a single interpretation or a single assignment of T's and F's, a single model, as I've been speaking lately, in which both of these things are going to turn out to be true, right? So there's a really easy one to test for consistency, okay? You just assign T's to both of these, right, to P and Q. Now, are both of these true? Yes! Okay, so you know that you can put consistency there, right? But now you got to figure out whether or not entailment holds. Now, entailment is the idea here. If we look back at our lecture, I think this is on semantics of assertion. An assertion P logically entails an assertion Q in the language if and only if all models of the language where P is true are ones in which Q is true as well. Right? That's the idea of entailment. Entailment is not going to hold if this is true, the first line, and this is false. Okay? So what you can do, right, is actually start with the bottom line and see if you can make it false. And in this way you do that by making the P false and the Q true. Now determine whether or not that particular model will make this true, right? If it does, then you can know that entailment does not hold, right? And if entailment doesn't hold, then neither will logical equivalence. Okay, so now it is the case, right, that you might have to put more than one property, right, given the well-formed formulas, right? So here I have that part crossed out, not down here. Okay, all right, good times. Right, you should be able to figure out whether or not these two can be consistent and whether or not entailment holds. Okay, right. I think this is a good example of when entailment holds. Right, look at this slide again. Right. Whenever whenever P is true, is Q true as well? Okay, well, let's look at the homework problem. Oh, that's the music. Sorry. Let's see. Okay, so whenever P is true, is this going to be true? Right, answer that question. All right. Now, if you can figure that out, you might want to think, well, does equivalence hold? Well, then you would have to figure out whether or not entailment goes from this one. Can this, whenever is this true, is this true? Right. Now here, this is the toughest of the bunch. I'm going to leave that for you to do. Okay, you're going to have to walk through all four models to figure out whether or not this thing entails this thing. Right? Right. I think you can probably judge that it's consistent, right? If you assign T's to both P and Q, well then everything's going to turn out to be true, right? So consistency is going to follow, but I want you to figure out whether or not entailment follows. And that's going to take a little bit of work. You're probably going to have to go through all four models to see whether or not entailment holds. Then you're going to have to figure out whether or not it goes the other way, okay? So you'll have to try to make, whenever this is true, right? Is this true? Or you can test for it this way. Try making this false and then making this true. Right? Okay. And remember, equivalence is just the idea that they stand and fall together. So if this is false, then this is false. This is true, then this is true. If you find kind of disagreement where one's true and one's false, well then equivalence doesn't hold. Okay, so on D, again, I want to draw your attention, right, to the fact this is looking an awful lot like this here, okay? And that is a logical truth. So you should study the slides, right? And ask the questions. Are logical truths consistent with one another? Okay. Do they entail one another? Right? Are they equivalent with one another? Okay, there should be obvious answers to that question if you understand these concepts, right? That's the real goal. Okay. All right, so here again, we're testing for validity. Now we did this kind of stuff on Friday. Okay, what you do, right, is you try to make the argument, you try to determine whether or not the argument is invalid. And if it's not, well, then it's valid. Okay, now we've gone over this ad nauseum as of late. Okay, but if you'll remember, an argument is valid in the logical language L if and only if every model in which all the premises are true is also one in which the conclusion is true. Okay. An argument is invalid in L if there is at least one model that makes the premises true and the conclusion false. So for these exercises, it's best to actually just start with the conclusion, okay, because you just need that one model to show invalidity. Now, you can't do it here because if you make P false, right, because that's what, that's what invalid arguments are, is conclusion false, true premises. You make the conclusion false, you assign an F to that. Okay, then you have an F up here. You make P true because you're trying to get true premises, right? But then you have a T here and an F here, which makes this false. Right? Now, that's impossible. You can't get it to be valid. Right? Or, I'm sorry, you can't get it to be invalid. So that means it's valid. Right? Now, just kind of revisiting one of the ways of thinking about validity here. Right? If the conclusion of a valid argument is false, then at least one of the premises must be false. And that's exactly the case in our example. Right? Remember, validity, it doesn't determine the truth of the conclusion all by itself. Right? You need true premises and validity to guarantee a true conclusion. Okay? That's what this first one is saying. Right? But validity is just all about form, right? You can have a false conclusion in a valid argument. That's possible. That's perfectly fine. But what that tells you then is that you have a false premise too, okay? And you must have it, right? So that is represented in our problem here. We have a false conclusion, but then we also have a false premise, okay? And so that is very much valid. Okay, not so here though in the second example. As you can see, right, you can make the conclusion false, right? So Q is false here, 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 right? This is an idempotent, so this is going to be true no matter what. Okay, now can you make this true given that you have a false antecedent? And the answer is yes. If you assign, right, a false to P, then this becomes true, and this becomes false, all right? And now you have the satisfaction of the definition of an invalid argument, right? You found at least one model, all it takes is one, that makes the premises true and the conclusion false, right? And we wrote that model down. There it is. P is false and Q is false. All right, so that's what we're doing, okay? So to do this thing right down here, I just want you to notice something here when you're doing the homework. You're gonna have a tough time making that thing false. Why is that? Well, it's because it's a logical truth. See, your tricky logic teacher is just such an ass, and he puts that in there to mess with you. Okay, so here's the thing, right? There's no way for you to make the conclusion false and the premises true. And so you can conclude, and you fill in the right answer, okay? All right, here we are with B. Again, okay, here it is. Now, I think we actually did this one in class as an example, so I'm just going to let you puzzle over that. See if you can make, though, the conclusion false, right? And both of these premises true, right? And then tell me what your answer is. Same here, okay? You should know how to do this by now, okay? There's one way for this to be false, okay? Can you make this true? I certainly hope so. All right, okay, so that's how you do that. And now we are on to the well-formed formulas of TFL and how to determine whether they are well-formed or not. I gotta pause it for a moment and pull up my slide. Oh, right, there it is. Okay, this is our nice recursive definition of TFL. Here you have predicates A through M, names A through M in lowercase, the different kinds of brackets you can use, the 5 different operators that are allowed, And then the rules, right? Any predicate followed by a finite number of names is a well-formed formula. And then any of those formulas, P and Q, okay, stand in for any of those. Those are going to be well-formed formulas. Then each of these, right, are well-formed as well. Right? So a negated formula, you have a conjunction formula, an or formula, a conditional formula, and a biconditional formula, right? And then nothing else is. Right? So given those rules, right, you just kind of slavishly follow them when you're looking at this. Right? And so if you look at the example here, you can see that P is not allowed in our alphabet, so that's not well-formed, okay? But this one is. This one's okay. This one follows the rules just fine, right? All right, so looking at this, right, you just have to determine whether or not things are obeying the rules, okay? All right. And you should pay attention to certainly the alphabet issues, okay? All right. Now here, you just have to be able to identify what the main connective is in these well-formed formulas. All these are well-formed, by the way, so you don't need to worry about that, right? So you need to circle the main connective. Now that in the homework example, it looks like I forgot to put the circle in there. I'll have to do that at some point. But I want you to circle the main connective and then underline underline its components, right? Not subformulas, but components. Remember, right? This is a compound formula, but it is a component, okay? It's being attached by the arrow. So you would circle the arrow and then underline just like so. Okay, here you have to identify the main connective. That's the ampersand. You underline the components and then tell me what type it is, conjunction. Right, and the trickiest things here is just to pay attention to the negations, and that's what's nice about this example is that we do pay attention to the negation, and we underline the component, which is this whole thing that it's negating. Right, so be on the lookout for those tricky negations. Okay, I think that you're pretty good at finding what the main connective is. It's just a matter of paying attention to the brackets and where they are and what they're doing. I have full confidence that you'll be able to pull this off. All right. So that is the homework, all right? It's a bit tedious on this section, I do admit, right? You will kind of struggle over this, but I think that's good. I think that you guys are due for a little bit of struggling, and I think it's good to struggle with these concepts, right? And work through the models. This is a very simple language, so I think you should be able to do it. Of course, right, if you have questions, just shoot me an email. I'll try to answer as promptly as possible, okay? And we'll see what we can do about connecting through Skype or something like that, if that is a problem as well. But you have my email, it's in the syllabus. This is the homework, and turn it in by 2:15 on Friday. That's when the last class gets out. I said 2 in some of the other sections, and that might be confusing. But get it in by 2:15 on Friday. That's when the homework is due. This, of course, is assuming that Clemson is open Friday. If it's not, well, just batten down the hatches. Don't party too hard. Have be safe, right? Make sure if you can help somebody who needs help, go out of your way to help them, right? That's the ethical thing to do. So enough instruction from me. Have a good time doing this homework, and I will talk to you later.